Today is the 18th of September 2017. This is our first lecture on single-phase fluid flow through porous media. And we can all go home now because everybody's already had this before and nobody cares, right? Wrong. So tonight what we're going to do is we're going to derive the very simplistic, simple, easy, no frills, liquid flow equations for what? For steady state, linear, and radial flow. Why? Today we had an email from the dean's office, and they're going to renovate a building, and they're going to put a facade on it, and they want to put the 50 most important equations in engineering on it, and I think we'll be assigned 2 or 3 based on the number of, relatively our department size and that sort of thing. So what would the 2 or 3 equations be that you would put on the building or on the facade? Okay, so the first one was Darcy. What's the second one? Second was diffusivity. And then it gets kind of murky. The faculty, except for me, of course, they like to show how smart they are, so they circulate, they copy all, they reply to all. And so they replied to all sorts of different equations, the equation for the energy balance. And somebody went as far as to put something like this long in there for calculating, bottom hole pressure or something like that. And I'm like, that's going to look really good on a facade. I'm sure that somebody's going to probably go, you got a sign or, or something like that. What was missing from that? Nah? Nada? You got nothing for me. Petrophysically, what's the most important equation? Sorry? Archie's equation. And so I sent it to the faculty and said, we ought to think about Archie's equation, expecting some smart aleck remark. And then the one person who specializes in that said, oops, I sent it to one person, thinking that they didn't want to expose themselves to the scrutiny of their faculty. So Archie's equation would be good. What else? I thought the deliverability equation would be good, or some of these, but they're derived from Darcy's law, so that's probably not going to get very far. Somebody suggested the relative permeability equations, whatever that means. Somebody suggested another energy balance equation. Is there anything else you can think of that we use all the time in petroleum engineering? Sorry? What? P equals rho GH? Yeah, I'm not real sure that one's going to go very well. Ladies, P equals rho GH is the equation for pressure. It's so density times height. Yeah, well, that'd go to mechanical if it went to anything. Anything else? Ooh, that's a damn good idea. Nobody said that. Can I quote you? Do I have to? And it'll be the extra long one, That would be so cool. It'd take up half the building, That is really a good idea. What about the IPR equation? Yeah, short, sweet, to the point. Yeah, that might work. I don't really think we're going to get any. Okay, just between you and me, this department always, and since this goes out public, I'm sure somebody's going to, I'll hear about it, but, we'll see. Any last thoughts? Sorry? Somebody suggested that. Very good. Very good. It's not really his equation, though. That's the hard part, But there were a lot of people that got credit for things that weren't really theirs, but it's all right. So is it more important that you come up with something or that you write the paper? Ooh, trick question. Are we all the sum of everything else that goes on in existence? Or do we have original thought? Neither. Somebody said. Last chance, Cameron. Juan? Is there an equation that's a crossover with something else? My personal favorite would be if somebody put phi v equals z in RT, but I'm sure the chemies would go nuts if we did that. Anything else? All right, we'll leave it behind. So tonight we're actually going to derive the deliverability equations, but it's not going to exactly be the deliverability equation. Why? Because the deliverability equation is valid for pseudo-steady state flow. Everything we're doing tonight is steady state flow. But if you derive an equation that looks like another equation in every way, shape, or form, what's your conclusion? And don't say they're the same. Just say they happen to look alike. So if you park a black car next to another black car, are they the same car? I don't know. There's assumptions, I know Gabe's going, well, if we had a black Hyundai Sonata 2015 and then a black 1939 Volkswagen Beetle, who can tell? No, I'm joking. Okay. But I think everybody realizes it could be significantly different. So this is a summary of all the equations that we can derive. Of course, we have our linear flow equations, and then we have our radial flow equations. And with the exception of the geometry term, which is really the distance term, which is the log of r over rw, as opposed to x, these equations have very similar forms. Now, of course, you see that when we look at the radial flow equation, we have an r here. Why do we have an r there? What's the cross-sectional area for a rectangle? Well, it's just that area at the end of it. What's the cross-sectional area of flow for radial flow systems? It's 2 pi r. Okay, so we got to factor the 2 pi r. So what is Cx and Cr? Those are the conversion constants, right? So for Darcy units, the conversion constant for linear flow is 1, which makes sense because that's how we defined it. For the radial flow case, it's 2 pi. Where did the 2 pi come from? From the 2 pi r. Okay, for field units, we talked about this the other night. We derived these coefficients. And then for SI units. And you'll notice that the field unit term that we derived the other night, multiply that by 2 pi, and you get that. The SI unit term, which we did not really derive, but we talked about, is there. And then that's the term that we would get when we multiply it by 2 pi. So what we're going to do is we're going to derive these side by side. Math ladies, this is really simple. Okay, I mean, this is like you can sleep until I wake you up. Okay, it's that simple. But there is a trick. What's the trick, class? What do we have to assume about viscosity? Constant. What do we have to assume about formation volume factor? Well, we never talked about formation volume factor, but formation volume factor is a mass-defined relationship that relates volume at the bottom of the well, or volume in the reservoir, and volume in the stock tank. We sell stock tank barrels, right? But there's reservoir barrels down there, so we have to account for their expansion. I'm explaining this because, ladies, you're always going to see everything multiplied by B. B is an expansion factor, okay? Its definitions are reservoir barrels per stock tank barrel, or it could be reservoir meters cubed over stock tank meters cubed. We always sell in stock tank barrels, barrels at the current condition, at the surface. So if we're going to sell a barrel of oil, it's going to be at 60 degrees Fahrenheit and 14.7 psi, and we're going to get X amount of dollars for that. But we have to convert that barrel to conditions back down hole, so we multiply it by B. And in this case, we're assuming that B is constant, which is not really true, but that's okay. So viscosity, formation, volume factor have to be constant. Why do they have to be constant? Steady state. If they're not constant, then they change with pressure. Does pressure change with time? No. But it introduces itself as a nonlinearity. How do we treat most nonlinearities? Cameron? Do you like get a bunch of bills at home and just throw them in a stack and not think about them again? Okay. Anybody else, bill comes, you figure what the hell, somebody else's problem. Well, if you were to say that, you'd be my wife, okay? Every time I go home, there's a nice stack of bills. But, like you said, I got them all done electronically, so that's okay. But there are a couple of times a month when the Amex bill comes on that internet thingy you were talking about, where I end up grabbing my heart, you know, that sort of thing. But I can't let it go, but some people can. So what happens when we have a nonlinearity? You can be like me and worry about it, or you can be like my wife and just ignore it. What happens when you ignore nonlinearity? Sorry? Okay, but what happens when you ignore it? I'm not saying what happens when you fix it. What happens when you ignore it? No, but what happens? Would you use a gas equation, or would you use the liquid equation for gas flow? Okay, you're still not coming in. I need you to come in and say it. It would be wrong. There's no way it can be right, okay? Now you said linearizing. I don't know what that means. How do I explain linearization to this group? Do you like chicken or duck? Chicken? You like duck, okay? So he's a chicken salesman and you're a duck eater, okay? So what he's going to do is he's going to put a plastic nose on the duck or on the chicken and some plastic feet on it, and he's going to sell it to you. And you're going to go, I got me a duck. And then you're going to want to show all your friends, right? So you're going to take your duck outside and it's going to, like this. And then what's he going to do, Cameron? Say, show me how you can fly. And he throws it into the pond. And what's going to happen to your chick duck? And it's going to sink to the bottom. And that's what's going to happen if you don't correct this. Linearization is a process of making the chicken think it's a duck. But you still have to make sure you linearize correctly or that thing's going to drown. Okay, we'll go through that in a minute. The first cases we're going to do are liquid only. Okay, this is a summary of all the equations we're going to derive. I know this is intimidating, but trust me, you can do this. Just as practice, I strongly suggest you derive all the relationships in here. I know that's like talking to the wall, but give it a try. So you'll start with a differential form, and then you'll derive the difference form using calculus. No problem there. You'll start, whenever you start with the linear form, you'll end up with this. When you start with the radial form, you'll end up with that. Now, it gets a little weird when you start to use pressure squared. Now, we talked about linearization. There's the correct linearization, which is defined something like pseudopressure. And pseudopressure makes the chicken really think it's a duck. It can swim, it can fly, it can do all sorts of other things, but it's still a duck. What is pressure squared? Pressure squared is sort of a partial approach. Pressure squared is an empirical approach to linearization. In the case of pressure squared, you have to assume, this is for a real gas, that the viscosity and the Z factor are constant. What conditions for which are the viscosity and Z factor constant? Mr. Desai? You're a chemical engineer, right? No. Do you want to throw a lifeline to a chemical engineer? He's sitting in front of you. Mr. Bake? How about an ideal gas? Okay. For an ideal gas, the viscosity and the Z factor are constant. Well, the Z factor is 1, right? So if we define the viscosity and the Z factor as constant, or the product of the two is constant, that's really almost an ideal gas assumption. So we'll see how that works out. Whenever you hear ideal gas, what bell goes off in your head? High pressure or low pressure? Low pressure. High temperature or low temperature? Low temperature. High temperature. All right. So I know this is complicated, and I do apologize. On the left-hand side of any given page is the linear, and on the right-hand side of any given page is the radial. So we start by defining our box, and our box is a parallel pipette. It's a rectangular box. The flow is towards the left. I like it that way, so I end up with a minus sign. This is the cross-sectional area. It's the thickness times the delta y. The delta x is this distance. X equals 0 is here at that face. X equals xe is over here. So we've got all of our reference points labeled. We're going to integrate from PW to PE. We're going to integrate against this. Same thing's going to happen for the radial flow system. It's a RZ configuration. R is increasing out away from the wellbore. There's a definition called RE. And then we have, of course, rate coming in. It's coming in uniformly around this circular perimeter, 2 pi r. Okay. And then when you look at it in a side view, it has a constant thickness H. It'll have linear flux lines coming into the wellbore, and it'll extend out to RE. And of course, as I've mentioned several times before, the cross-sectional area over which this is acting is 2 pi RH. The governing equation is Darcy's law in both cases. This is Darcy's law for linear flow. This is Darcy's law for radial flow. Okay? They're essentially the same. A sub r is equal to 2 pi RH. So you simply substitute that in, factor out the 2 pi, and you're left with r dp dr. Here, we're just going to let A be a constant because it is a constant. We're going to assume that this face is fixed. Okay. I got a little conservative with my use of space. I apologize for that, but I went on ahead and put the conversion factors down here. And this also goes a couple of pages away, but it's here for now. This is some definitions of formation volume factors. So we'll change this a little bit. We'll call it C sub r, which is the coefficient or the units conversion constant for radial flow, KH, B mu, R dp dr. So we're almost there. Now we start our solution. Linear flow is on the left-hand side. Radial flow is on the right-hand side. We start with Darcy's law for a given case. No surprise there. We're going ahead and make our assumption that the viscosity multiplied by the formation volume factor is constant. So we can extract that. We take it outside the integral, and we're left only with an integral from PW to PE dP. We're left with an integral from 0 to XE dx. We have an integral of RW to RE of 1 over R dr because of this. And then we have everything else factored out. In other words, the right-hand side of these two equations is exactly the same. The coefficient, of course, here is different, and there's a difference here that it's H and not A. But in terms of form, we end up with this integral being exactly the same. So now when we integrate this, integrating the left-hand integral in terms of dx, it's just xe minus 0, obviously. And when we integrate the left-hand integral on the radial case, it's natural log of RE over RW. If you were to do that as an exercise, I'd probably delete all the credit because you have to start with a definition. What's the definition of the logarithm? Who wants to take a shot at that? Math ladies? Natural log of x is? No, what's the definition? It's an integral. It's 1 to x, 1 over x dx, right? 1 to x, 1 over x dx. How do I know it's 1 to x, 1 over x dx? Alex covered this. If x is less than 1, the value is negative, correct? And then you have to know some rules of logarithms in order to add and subtract, but that's okay. So whenever you have the logarithm of a minus the logarithm of b, that is the same as the logarithm of a over b. Okay? That's where that rule comes from, or that particular form. I know this is trivial, but it's been a long time since you've thought about it. So you solve for the rate. We don't ever really use the solution solve for the rate, but we write it like this a lot. So there's the radial flow part. We can rearrange it and solve for the pressure at x at any time or the pressure at r at any time. Now this is radial flow and linear flow. The constant fluid properties. What do you think the gradient is going to look like? Who wants to take a shot? Ricardo? It's going to be a straight line for the linear case, and it's going to be a straight line for the log R case. Okay? But what about R? What is R going to look like? When you're looking at an equation like this, what's the pressure distribution? Well, let's look on the next page. See, I was ahead of you. So this is the linear flow case. Plotting it on a Cartesian plot gives you this. This is the radial flow case. Plotting it on a Cartesian plot gives you this. And then plotting it on a semi-log plot gives you that. Class, tell me something. Where is the highest gradient? What can you learn from this? Where's the highest gradient? At the wellbore, right? What does that mean? And then what happens out here? It just gets less and less until finally it's really small. Okay? I drew this to where it looks like it's 0, but it's not. Okay? The highest gradient in the radial flow case is near the well. Where's the highest gradient for the linear flow case? It's constant. So we've already had a small discovery. The small discovery is that for the linear flow case, we have a constant fluid gradient, or constant pressure gradient, pardon me, assuming constant fluid properties. And for the radial flow case, the highest gradient is at the wellbore. Seems trivial, but it's worth mentioning. Now, what would happen? What would happen if instead of assuming that mu b, the formation volume factor, and the viscosity were constant, if we assume that they were allowed to be just functions of pressure? No condition. Mu of p can look like a sine wave or a curly Q. It doesn't actually, it just goes up. And what's formation volume factor going to look like? Well, we're going to redefine it in terms of Z for the gas case. Okay. So the first thing we do is we multiply and divide the equation by mu I BGI. Sorry, I didn't say it correctly. We multiply through by mu I BGI. So we multiply both sides of the linear flow equation by that. We multiply both sides of the radial flow equation by that. Why do we do that, class? We're going to set a standard. Okay? Going to set a standard. And then the next thing we're going to do is we're going to isolate constant terms. QSCBG is actually the reservoir flow rate, and then mu dx, we move that over, it's mu I. And then we have our conversion constant, then we have Ka, and then we have mu I Zi over Pi, P over mu Z dP. We have QSC BGI, same as on the other side, mu I. And then we have this 1 over R dr, which is due to the geometry of the problem. And then we have the coefficient CR, we have KH, and then we have mu I Zi over Pi, P over mu Z dP. So the right-hand side of this term here and here are the same. So now we set up the integrals, and when we do that, we can isolate an integral here, and we can isolate an integral here. Okay? And I neglected to mention this, but I did sort of cheat. We use the definition of BG, which is back on the previous page. This is the definition of BG. It's the density at standard conditions divided by the density at any condition. Density is P over Z, MRT, these are gas constants, and molecular weight and temperature are finally this. So when we substitute that out, all we're left with is the P over Z ratio. So now we isolate this integral, and how many of you have read the first paper? What was the name of that paper? Who were the authors? Al-Husseini, Ramey, and Crawford. Very good. How did they define their pseudopressure function? they have 1/2, or is it 2? It's 2 multiplied by this integral, P over mu z. This is mu I zi over pi multiplied by the integral of P over mu z. We just defined this by fundamental principles. Why did they define their integral as 2 multiplied by that integral rather than mu I zi over pi? Did you read the paper by Russell Goodrich at all? Nope. Who was the first person to invent the telephone? Yes, I know it's a trick question, but go ahead. Who's credited with the patent? And who was 2 hours later? What was his name? Gray or Yale or something like that? I don't remember. You guys don't remember this? So I always ask this question when I do pseudopressure derivation. 25 years ago, I asked this question, and this Russian stood up and goes, "It was Dombrowski, but Bell stole it and patented it." I was, oh my God. How do you argue with that? Okay. So who defined pseudopressure first? Was it Russell Goodrich et al., or was it Al-Husseini, Ramey, and Crawford? And Cameron, you're thinking, I don't care. You want to throw a lifeline to somebody else? Ooh. Particular who? In particular who? It wasn't just Muscat. It was Evinger and Muscat, 1942 or 43. And when they defined it, they basically said, we can't calculate it, so it doesn't matter, which is okay. But 20 years later, these guys come along, and they have a spit-spewing cat fight over who invented it. And who won? Ramey did. And we're stuck with this stupid 2 multiplied by the integral P over mu z. Why are we stuck with that stupid equation, as I just said? Now, your generation doesn't care about this because it's all in the software. But my generation had to care about it. Because what are the units of that integral I? Sorry? It's P for pressure. Everything else cancels. Why is that important? Because if we'd have used that form, we would have ended up with exactly the liquid flow equation, only we would have used a different definition of pseudopressure. But instead, we use Ramey's definition, and we've got all this crap hanging along. And if you don't know what the crap is, look in any gas well testing book, and you'll see there's temperature and molecular weight and some weird constant 1422 and some other stuff. We could have eliminated all of that by judiciously defining pseudopressure in this form. Okay? Nobody cares. Great moment in history. Nobody cares. I love it. All right. So we go on ahead and calculate the integral, and we end up with something called P of P, P of P PE, P of P PW, and the definition of P of P is here. And like we said, the definition, this is the Russell Goodrich et al. Definition, and the Ramey et al., or the Al-Husseini, Ramey, and Crawford definition would just be a 2 out here. So, who wants to take a shot? Why did they put a 2 in front? If you integrate with mu z equal to a constant, you get p squared over 2. The 2's cancel, and you have p squared. So, the times were the reason they did this. Everybody was using pressure squared equation. So if they could make pseudopressure look like pressure squared, which is what that form does, then they had a pressure squared equivalent type concept. But the rest of us suffer. Okay, so we can continue to integrate and to carry forward and so forth. And here's the definition of rate for the linear flow system, definition of rate for the radial flow system, definition of distance, pressure versus distance, pardon me, for the linear flow system, definition of pressure versus distance for the radial flow system. Here's the pressure versus distance for the Cartesian system or linear flow system where the properties are constant. Here's the pressure for the radial flow system where the properties are constant. So pseudopressure and pressure. Pseudopressure at the well and pressure at the well. 1 over Cx, no big deal. QSC, no big deal. Ka, no big deal. B over mu, no big deal. BGI, mu GI, no big deal. So does everyone see the similarity here? Yes? No problem. Everybody got it. Same thing on the radial flow side. There is another approach to this, and as I was mentioning, I won't go through the details, but if we assume Musi is constant in the definition of pseudopressure, we end up with an expression that is basically defined as, you just keep working through the algebra, and, well, let me show what this looks like. So you end up with this being equal to this, and so you're going to have a TSZ over T, ZSC over PSC, 1 over mu Z, which is constant, 1/2, which we talked about a minute ago, PE squared minus PW squared. And again, that's where all that noise came from with the Ramey definition, because they defined it that way. So then the pressure squared equations are like this. You have one for radial flow and one for linear flow. Why are these equations so important? Somebody help me. What do they tell us? Distilling these equations down, and I'm going to go off script for a minute. So what happens when I plot rate on the x-axis? Actually, I guess I need to say log of rate. And I'll be lazy and say ln. And then I plot ln of P sub E squared minus P sub W F squared. I know that doesn't look very good, sorry, but I think you understand what I mean. What happens when I plot that? What am I going to get? What kind of a straight line? Sorry? Okay, so do we need to put some little numbers in here? I'm going to say log now. I cheated. I decided to change this. What is log? Log is log base 10, right? I'm going to make me some homemade graph paper. So we'll say 10 to the 0, 10 to the 1. Man, it sounds like you guys all got my cold. Good thing I gave it to somebody. Alex says he's sick now. You know, it's a gift that just keeps on giving. All right, so this is 3. This is 4. And unfortunately, I can't be lazy. I wish I could, but I can't. Did you guys have a good week, though? Did you do anything interesting? Nobody's talking. You're bringing me down. And I'm just making up numbers. Do I have the same number? Yeah. You guys don't like me drawing my own graph paper because it's really slow, right? Just wait till you get old. It could happen. Anybody see any good movies lately? Somebody watch It? I heard it scares the hell out of you. Is that right? Really? You don't like that sort of thing? Did you latch on to your date? I knew you were going to say that. I'm just going to drop it because I don't want to go to jail, so, or lose my job. Being politically incorrect is my specialty. What do you think of College Station? You can say the truth. Huh. Let me give you a hint, guys. There's a hell of a lot of you here now. What's your favorite color? Blue. That's pretty. So we're going to put some points on here. I got to come down here a little bit. What kind of line is it going to be? What's our favorite kind of line, class? What's our even more favorite kind of line? A horizontal line. But this ain't horizontal, so that's kind of a trick question. How do you make a unit slope line? You put it through the corners, right? If I've drawn it correctly. Sort of. Not perfect. Okay, so we shove that line through there. Wow, that looks pretty good, Tom. Okay. So we come back over to this equation, and we have rate down here, and I don't really know why they put rate on that side. And then we have pressure gradient, or sorry, pressure squared over here. That's there. So we sort of flip it. And then all this other stuff's a constant, right? What's the slope on this thing? It's 1. Okay. So this is a unit slope line. I guess I should write slope of 1. Is this the oldest reservoir engineering equation? No habla English? Pressure what? Thank you. Did you guys read the Rollins and Shellhart book? Did I not include the Rollins and Shellhart book? 1935? Sorry? Oh, no, I thought you'd like that one. I got that one off that internet thingy. I didn't give you the Rollins and Shellhart book to read? That would have just been mean. Oh well. The Rollins and Shellhart book is something we go over in well testing class. The entire book is devoted to that equation. 1935. Now, why did pressure squared work in 1935? We talked about this before. Why? Low pressure. Okay. What was our depth that we could drill? Maybe 6,000 to 10,000 feet at the most. Okay. Let's take a quick look. These are all a bunch of graphs, and I'm sorry for their small size, but it's important. This is mu z versus p. Mu z versus p. Mu z versus p. Now, I know this is a complicated concept, but this is probably not horizontal, correct? Class? Do we agree this is not horizontal? Okay. But funny thing happens whenever you take the logarithm of it, the first part is horizontal. Now, a lot of people say, oh, but that's because there's only 1 point here and 1 point there. Nope. There are 100 logarithmically spaced points here. So there are 100, there's 50 that define this line. This is an empirical observation that the product mu z versus p is essentially constant when you're looking at it on a logarithmic scale. Of course, then it takes off, right? Cam, based on that red horizontal line, can you say that mu z is approximately constant until 2000 psi? Okay. Anyone else? Alex? No? You don't think it's constant? You want me to make it bigger? You sure your name isn't Thomas? This is mu z on a logarithmic scale and pressure on a logarithmic scale. This is a sort of horizontal line. What do you think now? Now, I understand some of you are going, well, it can't be constant on a logarithmic scale because it has to be constant on a Cartesian. Constant's constant. Okay. Is that constant enough? This was a big conclusion in Ramey and Wattenbarger, right? That for pressures less than 2000 psi, the pressure squared method was sufficiently accurate. Why is this important? Because if you can use pressure squared as your pressure variable, then you don't have to calculate pseudopressure, which is a big savings. You don't have to carry around a bunch of things that you don't know what they are. Now, since we played this game, this is the product mu Cg, and this is pressure. In other words, this is the viscosity multiplied by the compressibility. Is this constant? Sorta. Sorta. Not really. Sorta. No. Okay, so I can't fool you. But Wattenbarger and Ramey said for pressures greater than 4,000 psi, P over mu z was constant. Do you agree? it looks constant, but let's take the logarithm of both scales. So this, is that constant? I don't think so. Is this constant? Sort of. No, 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 right? Why is that important? If you're going to create an equation or a condition, I should say, where you assume something's constant, it better be constant either over the full range or from the point where you say it's constant back to zero. Saying something's constant greater than something else doesn't help you. Reservoir pressure doesn't go up with time, it goes down. So this, if you say, well, I can use pressure to represent gas reservoir behavior, this equation or this concept, it deteriorates for the lower pressure that you have. Now this is important later, and I apologize, I've kind of thrown it on you, but we're going to talk about how to derive pseudopressure and pseudotime. The pseudotime condition is that you have to integrate mu-CT as a function of pressure. And what you're figuring out right now is that mu-CT is never constant, which by induction, if you have to have pseudotime for mu-CT not constant, and mu-CT is never constant, then you must always have pseudotime if you're going to use a transform variable. This is where it breaks down. You have to know the answer to get the answer. Saying that mu-Cg is a function of pressure is all good and fine, but pressure is a function of time. The integral is in time. Therefore, you must know what? Pressure as a function of time. What are you trying to solve for? Pressure as a function of time. So this only works for buildup case. Okay. What happens in a buildup case? Well, we'll talk about that. Any questions? Everybody's okay? Steady state, radial, linear flow, constant fluid properties, variable fluid properties. Okay, pseudopressure. Here's a quick and dirty derivation of the pressure squared equation. We have a 4-rate test, or as we call it, a multi-point test. And then we have an extended zero. So each one of these, the pressure flattens out, although it doesn't really. And we can relate this pressure to this rate, this pressure to this rate, this pressure to this rate, this pressure to this rate. So you have 4 rates and 4 pressures. Now, if you had to say how to read this, you know, there were some old rules of thumb. And one of the rules of thumb was that the pressure isn't changing more than 1 psi over a certain time interval, 30 minutes or an hour. But we all know that's not really what happens in the reservoir. So conceptually, this is a little off, but in practice, it's used all the time. So we'll have the logarithm of the average reservoir pressure squared minus the wellbore pressure squared. That function will be plotted against the gas rate at standard conditions. And the reason that we do it this way is that if we say that PWF is equal to 0 or atmospheric, then we can simply draw a line across here, carry it over, and then carry it down and read off the so-called absolute open flow. What is the absolute open flow, class? There's no magic here. This is just a graph of data. The absolute open flow would be the theoretical maximum flow rate. So when you read the newspaper and it says that so-and-so has a new gas well and its AOF, its absolute open flow, is X, is that a real flow rate? No, it's calculated. So you have to be very careful when you're looking at other people's data whenever they report absolute open flow. Why does the government care about absolute open flow? I know we talked about this. No? Louder? Okay, that's good. It can define a variable or some sort of measure of productivity. Let's say that you own a well and you run a 4-point test and you get an absolute open flow of 30 million cubic feet a day. Ricardo next to you runs one and he gets an absolute open flow of 3 million a day. Okay? Ricardo is not going to be very happy with you because you're actually stealing his gas. You're producing at a much higher rate, and we all know there's dynamics, so he's stealing your gas. So Ricardo says to me, the purpose of government is what? Thank you. To protect and defend the rights of the people, right? One of your rights is not to be stolen from. So along with income tax, yielding reserves analysis, early reservoir engineering, along with pressure squared analysis leading to absolute open flow, the government comes along and says you must every year report your well's maximum deliverability, absolute open flow in Texas. Every gas well in Texas has an absolute open flow test once a year. Now, it took 4 points to define that line. Alex, where are you from? Really? Let's pick on somebody else. Cameron, you're like from Pennsylvania, right? How many points does it take to make a straight line in Pennsylvania? 2. Yeah? Well, there's 4 here. How many points does it take to make a straight line in good old Texas, Alex? 1. All you have to do is 1 flow and pressure measurement, and then what do? You put a 45-degree line on it. Why is it permitted to use a 45-degree line? Because that's the most conservative line. Okay? You can run a full test. It's not going to be fun, so everybody just runs a so-called 1-point test. Okay? All right, I think that's enough for that. You can continue to work through the algebra, and again, looking at it graphically, once you resolve it, you end up with this expression, which looks and smells and tastes just like the steady-state flow equation, doesn't it? Except there's one small but very important difference. What's the difference? Show me a hand of a petroleum engineer. Mr. Sarkar. In the steady-state case, the external pressure is fixed. In this case, we cannot refer to the external pressure because we don't know what it is. We refer to the average reservoir pressure. Subtle difference, but also very important. So we have to actually use average reservoir pressure. That's one difference. What's the other? Here we can have the n value be anything. For the steady state case, when we derived it, the n value has to be 1. Okay? Now, why is all this so important? Again, it's sort of the building block equation for rate predictability and so forth. Okay, then here's a bunch of other algebra. My apologies for that. We'll talk very quickly about the skin factor. Oh, should we do this the easy way or the hard way? What's behind you, Eric? No, that other thing. Bring it up here. No, that thing. The big thing. Don't say what it is. Okay. Set it right here. Now, what is this, class? Stay with me. No, this is a skin factor. Why? Because it's full of stuff that we don't want to know what it is, but it's actually a trash can. It's a pressure drop on our system. Now, do you want to know what's in the trash can? Do you want to know what causes it? Mathematically, we're going to define a skin factor as either A, a variable permeability, or B, as a fictitious thing, right? So how would we define it, Eric?
It's a pressure drop.
It's a pressure drop, but it's a trash can. So what possible things could cause a pressure drop at the well? Asphaltenes. Damn it. What kind of damage? Mud. Okay. Ladies? Gas blocking, water blocking. Very good. Very good. Okay. Flow geometry, slant, partial penetration, etc. Okay. Ooh, condensate dropout. He just said that, but we'll give you that. He said drilling. You said completion. That's a really good point. So you could pump some crappy completion fluid in there, pump scale or crap into the formation. Okay, good. High velocity flow can cause a skin. Very good. Next. That's all right. We're running out of things. Who wants to go? Yes? You already said that, but same. Okay. You know, you already had your turn. Okay. No, I said anybody on that row. Yeah, I know you did. So what I'm going to do tomorrow night is bring a roll of duct tape, and you can have the. Anybody think of anything else? I'll buy that. Who said paraffin? Okay, paraffin. Anybody else? Sort of ran out of ideas. Sorry, sand. Okay. So let's see what's in the trash can. Well, we got some pizza. We got an old cup. We got some paper. You know, I did this one time in class, and somebody had thrown away an unopened pie, and I opened it up and started eating it, and people were, you know, having convulsions and everything. Do you really want to know what's in here? You would like to say, I know it's perforation damage, or I know it's asphaltenes, or I know it's geometry, or I know it's something else, right? But in the end, it's a pressure drop. Is it one thing, or is it a bunch of things? Ooh, hadn't thought about that, have you? It could be multiple things. So what we'll talk about in just a moment is a very simple calculation of a radial distribution of permeability, and then just made something up. We're just going to say, we don't care what it is, it's a pressure drop. And we're going to assume it's constant. Somebody said condensate? Where was that? Okay. So what about a moving condensate bank? Is that a skin factor, or is that something else? That's something else. That's more like a radial composite system that's moving. Okay. But just blockage at the well, that could be condensate. Anybody think of anything else? Anything else? Okay. Nobody said cement damage, which I guess is kind of stupid, but I guess that could be true. All right. Do you want to take the skin factor back to the back of the room? Thank you. Okay, so we start with this diagram. And in this diagram, we have two distinct systems. You guys like donuts? You know what donut is? Ladies, you know what donuts are? How come donuts have a hole? Because if they didn't, they'd be a Danish? Oh, I don't know. How come donuts have a hole? How many of you watch The Simpsons? So you can put them on each finger, right? All right. So this is a donut. The outer donut is the reservoir. Then there's another insert donut that has different properties. Sort of maybe like a jelly insert or something maybe. And the properties are fixed. That's important. The properties are fixed. There's two possibilities. The flow behavior outside of the donut is better than the flow behavior inside of the donut, or the flow behavior inside of the donut is better than the flow behavior outside. Now, what we call that's permeability, but we'll just leave it at that. So the permeability outside is better than the permeability inside. Permeability inside is better than permeability outside. So if the permeability inside is worse than the permeability outside, we call that damage. If the permeability inside is better than the permeability outside, we call that stimulation. The very, very simple model. Who uses this model in the universe? Nobody. it's steady state. What is it? Kraft and Hawkins, demonstration model. But we can learn a lot from deriving it. And so what we'll do is we'll define the ideal pressure as this trend, and it'll be exactly the same on the lower graph. And then we can have a little piece like this. So if the permeability inside is lower than the permeability outside, then the pressure drop will be greater, right? If the permeability inside is better than the permeability outside, then the pressure drop will be less, right? What's the absolute best case for this model? Class? And what would that be caused by? An infinite permeability, right? So if you're going to use this concept to describe acidizing, and you put so much acid in that the permeability is now infinity, the best skin factor you can get will be defined by this. Okay? But on the other hand, you can change the permeability inside of this zone to where it drops the pressure to 0. So conceptually, there's a maximum amount of goodness you can do. You guys remember Lilo and Stitch? When the little girl painted the cartoon and said he had that much badness. How much badness can this have? Infinite. You can kill it. Okay? If you make the permeability of the inner zone low enough, the pressure drop, or the pressure just goes to 0. It's a maximum at the well. If you make the permeability high enough, it goes to infinity, the permeability goes to infinity, then the pressure at that second point is equal to the pressure at the wellbore. So we'll use steady state flow theory like we've already done for radial flow case, and we'll integrate the two pieces. So we start with Darcy's law, and we go on ahead and we set up our integral. We're going to integrate across the skin zone, and then once we do that, we'll define our skin zone relationship, and then we'll define a pressure drop across the skin zone. And we're also going to have a pressure drop not across the skin zone. And when we sum these up, okay, then we put them together and we have the actual pressure and the pressure at S here. And that's going to be 141.2, which is that number we derived, that 0.007808. The reciprocal of that, QB mu Ks times H, natural log of RS over RW. Is this a real equation, class? Can you calculate the pressure at point PS using the pressure at the well? Well, yeah, you can, but you have to know the permeability and you have to know the distance. So that's what we call an indeterminate relationship. We would have to assume that the distance that it propagated out in the formation is 1 foot, 2 foot. What's the farthest you think that filtrate can invade? Just off the top of your head. A couple of feet, probably less. But it can be really, really nasty. It can damage very, very heavily. So R sub S, I guess you could just say give it a maximum of 2 feet or something like that. But then you've got to know the permeability. Uh-oh, that's the whole point of doing this exercise. So you're still indeterminate. But we can write an expression that is the difference between the ideal pressure at the wellbore and the actual pressure at the wellbore, and that's PS. And when we do that, and we substitute all our relationships in, then PS is equal to this. And what I need you to recognize is what happens when K is equal to KS. That's 1 minus 1, and this whole thing goes to 0, right? Or more to the point, when KS is equal to K. Why is that important? That just tells you that the skin factor for the case where the permeabilities are the same is equal to 0. Okay. So then we don't like to carry around all this 141.2 QB mu over KH stuff. So we're going to define what's called a dimensionless pressure. This is your first time. So this is KH over QB mu, 141.2 in the denominator. That the dimension of that is dimensionless. There is no dimension. So that's K divided by KS minus 1, natural log of RS over RW. And so if K is equal to KS, the skin factor is 0. If KS is equal to 0, the skin factor is infinity. If KS is equal to infinity, then the maximum skin factor is negative RS over RW. And that's a relatively small number. So my point is, if you're going to believe that you're going to do something with acid, you're going to have to inject an ocean of acid in there to make the permeability infinity. Okay. Very quickly, and I'll quit after this, we're going to go on ahead and assume that we can use the concept of a constant skin factor added to the radial flow solution. And I apologize for going through this really quickly, but we're basically not going to make any assumptions about S. It's just a constant that we're adding on. It is, Eric, the trash can, right? We don't care what's in it. We're just going to mathematically manipulate this. So when we go through all of this mathematical manipulation, it says that the apparent wellbore radius is equal to the wellbore radius, the actual wellbore radius, multiplied by e to the minus s. Okay? If s is 0, then they're the same. If s is a positive number, what happens? Then you take the wellbore from being this diameter or radius, and you reduce it to something smaller. Is there a maximum smallness? It just goes essentially to 0, right? On the other hand, what happens if we have a negative skin factor? Negative is positive. Okay. What's a decent negative skin factor? Well, naturally fractured reservoirs tend to be about -3. What's a hydraulically fractured well? -5 to -7, but not much higher than that. And that is assuming that you can model a fracture with an expanding radius wellbore. And this is exactly what had to happen whenever Wattenbarger and Ramey were solving the wellbore storage problem that we'll look at very late in the semester numerically. They couldn't model a fracture at that time, so they modeled a very large wellbore. And that gave them the same effect. Okay? So that's pretty much about it. Please read through all of this. And tomorrow night we will cover the steady-state non-Darcy flow material. I know it's not on the, I need to send you an email, and I apologize I didn't do that. But I need to meet with you tomorrow night, and then Alex will meet with you Wednesday. I was going to meet with you Wednesday, but there's been a complication. So I'll meet with you tomorrow, and then next time we'll meet, it will be October 2nd, but Alex will meet with you Wednesday night. I guess he can also meet with you Thursday night and finish out the math lectures, and then we're ready to finish this other stuff. So we're in a really good position relative to the SBE meeting and so forth. Remember, I'm on home leave next week. So, again, send me questions. Hopefully everybody's working on their reading and their homework portfolios. If you have questions, just send me a note. I'll answer. And do I owe anybody anything? Not that I'm aware.
Rating portfolio is 1 page per page.
I would prefer it stay 1 page per paper. In the springtime when we did it, we had a couple of people that went a little crazy. I mean, if you want to go more than that, it better be, Well, I know, but some people, they really get into it. And my advice is if you think you're going to go more than one page, then reduce the font size. Okay? But stay on one page per.
So what is the detail you want?
That's the next question is again, some people went absolutely crazy and, they were giving all sorts of opinions and other things, re-deriving the results. It's yours. You do whatever you want with it, but you owe me a minimum of 2 bullets per topic. And they better be reasonable bullets, not this is bullet 1 and this is bullet 2. I did have people do that. Don't test my patience.
It says on the syllabus like poor to fair work will not be accepted. So
That would be poor to fair, yeah. Um, I had some other people that, wrote just absolutely silly things like, I couldn't think of anything or this isn't relevant. There's always something relevant. I know some of these things are tough. Some of them are easy. Just do me the courtesy of giving it a good try. That's all. I don't expect a work of art, but I do expect something reasonable. If you're going to do 3 pages per, congratulations. That impresses me. You'll get a nice comment whenever Alex and I review things. We put comments out to the side. So if somebody does a really good job on something, then we might give them some consideration. If somebody does a really crappy job on something, you can bet you're going to hear from us. So just treat it kindly. Now you need to be starting to work on your homework portfolio. Don't let that get ahead of you.